All right, we got a pretty long question, but a pretty short answer, so bear with it. All right, and the statement is, in a discussion of motional EMF, I assume that the wire loop has resistance big R. The current generated is then I over VBH over big R, okay, where EMF over R from Ohm's law. But what if the wire is made of a perfectly conducting material so that R is 0? In this case, the current is limited only by the back EMF associated with the self-induced or self-inductance L of the loop, which would ordinarily be negligible in comparison to IR. Show that in this regime, the loop, mass M, executes simple harmonic motion and find its frequency. All right, let's dive on in. Ohm's law says that V equal IR, so I is equal to V over R. So with respect to EMF, the curly E is equal to VBH, and thus this is related to the self-inductance via EMF equals negative L di dt, and force is equal to IHB, so we can find I from the force equation. So force is equal to HB, and the force is, Newton's law says that that's equal to MA. Okay, so now that we have a way to relate the self-inductance, the current, and the current with the force, now we can go ahead and solve for what we want. Substituting these in and solving for V, okay, back from EMF, we see that we have VBH is equal to negative L d by dt of the I that we found from the force equation, okay. And you see that the only thing that matters here is that A, which A is written as dB dt, so we see we have a second order derivative with respect to V. Okay, so VBH is equal to negative L over M HB d squared V over dt squared. Okay, now if we divide the B and H over, what we see in order to find the standard form for a differential equation, we have d squared V over dt squared equals negative H squared B squared over ML V, which has the form of negative omega squared V. And so with that, we know that omega is equal to HB over square root of ML, which ironically, we kind of see a similar result later in chapter 8 as well. So worth looking over again.